So far, I've talked about how is it that in dynamical situations you can end up in small finite dimensional manifolds, embedded into high dimensional spaces. Now I want to do another thing that all of us want to do very often, and this is how do we get close to the desired state, or how do we know that we are close to the target of our desires? And in America, little kids are always complaining, are we in Las Vegas? Are we there yet? How long is this car ride gonna take? So that's where "are we there yet" comes from. So a physicist typically preempts me in his lectures by introducing spherical cow, even though a week ago, before Matteo gets started, I had a spherical cow already, but I'll overlook this. This is the difference. Spherical cow approximation. Real neuroscientist takes a model which is physiologically correct, which is a cubic cow. If you Google, there are cubic cows that really do exist. And this is a container for a cubic cow. And I'll start with that. So here is my model.
The point of the cow is not too scary. This is important.
That's right, just to make you feel comfortable, mother's milk and all that. But so I will use a picture which looks like little squares and cubes, just to organize our thoughts. And in fluid dynamics and quantum field theory, this is actually the way people think. They say, well, I cannot solve a field theory problem, but I can discretize it and try to solve that problem, and then, show that in correct limit, I'm getting correct stuff. So for me, just the picture, there are little neurons or cubic cows, and each one of them has a name, and then there is a network of their connections. And the simplest network, which people are familiar in discretizing various problems in physics and engineering, is, producing networks in which everybody has two neighbors about each direction and stuff like that. And you think of this as the floor, on which the cows will be dancing. And it gives you some kind of geometry of who talks to whom. So it's a network, and you're very used to it in this school. You really think of this as an architecture of how neurons are connected and put together. I have a thing that, is a deep truth that I cannot explain here, that you should always include time as one of your coordinates. In other words, you should think of the world not in a photographs, but in a videos. You should think of things that can happen in a time sequence as well. And the reason, is intuitively obvious to many people, but it's much more robust to have information about a bit of a, emotion than just one snapshot of several snapshots. But for this talk, you can ignore it. But anyway, calculations for me are done in space-time. So now on this floor, hypercube on this floor in 2-3 dimensions, depending on the problem I am working in, I'll take a region, and I will record a relevant, important property, a set of properties of every node, every neuron on it. And that's what's, very romantically plotted here. This surface are the values of, let's say, firing rate or whatever at a particular site Z. And typically I have to do this over finite regions. In physics, I can make regions infinite, but in brains, we take finite areas. And when I have a point here, for me, this whole state, this whole disposition of fields is a point in a high-dimensional state space. And that we already have done when we discretize fluids. We were high dimension, and whenever I showed you a picture of vorticity down the pipe, one picture, there's actually just one point in million-dimensional state space. And the reason why this is useful, because in that million-dimensional space, dynamics is simple. Whereas, in the original space, it's very hard to analyze it or understand it. So now this lecture is about following question. This is very romantic, but what happens is I have this network and there's some activity all over the network. And I can, for example, instead of using the height and writing the surface, it's a very rough surface. Maybe it's easier to use a heat map and saying, if it's red, it's very active, it's blue, it's not active, etc. So I can think of this network as some kind of array. Again, it's easier for me to draw it as a square or square array, but it doesn't have to be that, in which every node on this array or in this graph has some activity which maybe I code by color just to be able to visualize it. Now, what happens in this, it's very much like neuronal recordings people show you from, array of 100 things stuck in the motor cortex. It looks like God knows what. You see it once, twice, and you can make sense of it, right? So now I would like to find out the following question. I've shown you this array, you have that array. Are we close? Are we looking at something or it's very different? So what is the notion of closeness? So that's, the subject of this lecture. There is a stupid idea that everybody will always do. Yeah.
And the question, what are the axes in those diagrams?
Yeah, so in this particular example, I'm really thinking along this kind of, in the bathroom, I have tiles, and on each tile I put something, and and that makes sense in physics. It doesn't necessarily make in neuroscience, right? So this is something I can draw, which is supposed to be an example of a network. Now, the typical network in neuroscience will have vertices or neurons with different number of connections to neighbors, etc. But there'll be some notion of near and far neighbors. Yeah.
What is representing field?
Excuse me?
What is E representing? The field, the vector?
Oh yeah, the capital phi is the entire configuration, and in this case, even an entire video. So if it was just space, then I would read off all the bits of my picture, and I would stack them up. So I have 10, a megabyte of numbers. Each one of them will be one axis in a state space, and that's two ways of thinking about a system. One is, there are lots of neighborhoods, and they have some activity, and this color says what the activity of the neighborhood is, and putting it on this, yeah.
This is a two-dimensional array of neurons. That's the way to think about it, and you're coding.
Yeah, you should think of it as a very rough, simplest possible thing to draw on a piece of paper that has structure of a network of neurons.
Okay. But each square is a neuron.
each square is activity. Yeah, each square is a neuron,
And color-coded.
and color is its activity. And it could be seven. It could be 7 dimensions or colors or whatever assigned to each neuron. But simplicity just what we call a scalar field. Just assign one. Yes, Kaylin? Yeah, in my world, it's an entire space-time video. So I digitize. If you have a 5-minute video of somebody darting around, it would be the entire video would be one point in that state space. But it's okay to think of it as being at an instant in time as well, if you want to. Yeah, in this particular case, it's actually one-dimensional chain of neurons, and vertical line is what happens to them in time.
Okay, so it's like.
Yeah, so every horizontal slice is an instant of this network. And, I can't draw million-dimensional networks. So all I do is I draw hypercubical cows instead of spherical cows, but that's about it. Yeah. Yeah, you can, in your plots, for some reason, time goes down, but I'm optimistic always goes down. So time goes up. What?
Yeah.
Well, there are various things, but it's not important for this talk. It just says, there is a pattern. And the question is, you give me a pattern, are they related? Are they close? Are they far? How am I going to think about it? So here is a stupid idea that we all do, has no justification whatsoever. It's saying, I have this network, I record the activity on every node. They're labeled by letter Z, they're labeled from 1 to many. Then you come with your activity on the same network. It's the same mouse brain, but, at a different instant in time. So that's, capital F is the all things that are happening at time 1, and, million things that are happening, and the other one is at time 2. And now the simplest idea is, we just subtract the 2. And we have this optimistic idea that if they're the same, it'll just give me a 0. And if they're not the same, they'll give me some number. Now, the real systems are noisy. So, there'll be some bound on how low this number can be due to noise, but I'll assume it's a deterministic system, no noise for a moment. Now, problem with this way of thinking is it truly makes no sense whatsoever. The network has all kinds of interesting topology, the manifolds, this, there. And you're just saying any distance in any direction equally good. It's Euclidean space. Why would you do this? I have no idea, but that's what everybody does, right? So you say, well, I measure the distance and it's 1.3 millivolts square because I measured some activity millivolts. And I said, well, no, but, I was using dopamine and something, and, I got some other thing. So, we are no place. I mean, it makes no sense, but that's what everybody does. So let's do it better. So doing better requires a little bit of thinking about probabilities, how likely certain configurations are. So what we can do is we can either have a theory that produces all these states, and we can measure how often a state shows up when I produce it. Or I can, try to do it theoretically, so I can assign a probability that when I look at my bathroom floor, I see with some likelihood half of it's green and half of it's red or something. I can assign a number to this, a probability how often that happens, and when I look at different floors. And then when you have a probability of configuration, you can generate all the configurations by going to your state space and just varying all possible activities. Each set of values is a point in the state space. So they generate all possible configurations. And, you know, if I have this prescription for doing assigning probability to it, that's called a partition function. A very simple thing to say, but very hard to do. Now, the way you think about it is you really, you know, I really think of it as a field. There's a floor, there's a grass growing, and, you know, the blades are tall, short, green, yellow, whatever. And I studied a region of it, and, you know, I'm interested in how likely I'm to see green grass in Eresfjord as opposed to the yellow grass in Eresfjord. Now, the next thing I need is the law, which comes cheaply in physics and comes very dearly in neuroscience. And the law says, oh, sorry, I haven't, oh, because I have to spot myself at some point. What do you say?
Did you scare the cows when you took that picture?
No, they were very happy. They came, you know, they came toward me curious. No, I was not one of the criminals who were. So, you know, in physics, the law basically says, you know, I'm a blade of grass here, and I look to the left, this guy is taller. I look to the right, this guy is shorter. And I remember by yesterday I was shorter, but tomorrow I'll be taller, right? So that's, you know, local configuration. And the law says, you know, on average, you all must be 7 or you know, something. So that's a typical law. I won't write it, you know, if you really want it, I can give you examples, but you know it. And in a subject like neuroscience, you know, you try to statistically find out what's the likelihood of what's happening. But this is not deterministic. It just says, you know, if this one does that, and I do that, that one can only do one thing, and that's called determinism. For example, if all these cows are looking up, the upside down cow is forbidden. You know, Norwegian law does not allow upside down cows. De er forbudt. So that's an example of the law. I can't do much more, but the main thing for today is deterministic. So every neuron has its law, and it's just one law. It's deterministic. That it might vary from region to region, neuron to region. In physics, it's always easier because, you know, it tends to be homogeneous, etc. Yeah. That's the law. What it says. Yeah, so it says if I have a configuration and I sit on one, you know, stand on one tile in my bathroom and I look, you know, out tall and the grass that's growing in my bathroom, whatever. The law says that if, you know, it's determinism, you know, it's forward in time. If I was in this state and my neighbor to the left were doing that, and there is unique result next step in time. And if I put the values of everybody on the left-hand side and write it equals 0, that's the way to write the law. You know, usually write law, you say the change of velocity dt equals, you know, a gradient, which means compared to neighborhoods plus something. Now put everybody on the same side. Now it's called the law. So it was invented by Feynman. Yeah.
Is it good to say that you have 5 things that I'm going to consider based on lower dimensional quantity?
They're very, you know, so there are 2 variants of this. In this case, they're totally constrained. That is to say, there is only one way. If I have 4 of them fixed, there is only one way I can get the 5th one in.
Yeah, then I can solve one of the components of the function of algebraic.
Yeah, so that's called, like, when you integrate forward in time an initial value problem, that's what you're doing, you know. you're giving in PDEs, you're given the value at a given time, which means you're given the various gradients, etc. The instant in time, and then you advance one step in time. And in determinism, there is only one way to do this. Now, if I take all the terms in your equation and let's put them on the same side, then I get 0 on the right side, and that's the law. The main thing is that the law has to be satisfied every place locally. It says wherever I am, I have to make sure that my neighbors do the right thing, or I do the right thing with respect to neighbors. That's called determinism. There is only one way to do it. Often, one can put weak noise into the system, so make it fuzzier, lots of stuff. But I will just take the deterministic law. That's what this Navier-Stokes equation was in the beginning. You start with some fluid. There is only one possible distribution of fluid 1 second later. So that's what I have in mind right here. The reason why I do this is because this is very rigid, and I still get stuff that you get in neuroscience. Go ahead, Lara.
So can you give a name to that? What is F1.5 connected to 0?
Yeah, so you've learned it in continuum as Euler-Lagrange equations in mechanics. And you've learned it in, other, it tend to be various equations. In this particular case.
Would it be like to think like the Navier-Stokes equation that you presented at the beginning? Like
Yeah.
putting all the terms in the left?
Absolutely, just put them on the same side. And Feynman says this, I can write every law of nature this way. What is it?
In this case, which is the name of that? You don't have.
In this case?
The law.
The law, in this particular, if it's in a hypercubic lattice, I said, it's a discrete version of Euler-Lagrange law, which says that, my solution, if I vary it, I'm only allowed to vary it according to the Euler-Lagrange, that's what classically, deterministically is allowed. But for purposes of this talk, this is just a formula, some polynomial, these neighbors, etc. That has a property you can take a derivative, because that's all I'll do. I'll take a derivative. But what it means is I just have to march according to the law. Yeah.
So C, that's like a standard for P1, P2, all of these different potential trajectories.
Yeah, well, so this Z is the index that labels the neuron or the tile or the point in a network.
Yeah.
And each one of them has a law. And if you're lucky, it's the same law. That's called physics. Then it's really easy. You use Fourier methods, this and that. If you do real stuff like neuroscience, then there might be a region where law is approximately the same, but the other region might have a different law, etc. Right? Because you have a heterogeneous, you're given a heterogeneous world. But I'm now, to start with, I'm assuming this law, you have produced a model that predicts this law exactly. And, you might mess it up later by adding noise to it. But right now, we want to find consequences if I do it exactly. So now comes, what does it mean exactly? If I'm in a world of all configurations, these phi's, most of them are not allowed. This is like watching, Stephen Wolfram simulate the world of cats, and you're going away from cats, etc. Most of these guys are just not allowed. Cows up and down, or cows that don't look like cows, they're just not allowed, right? In determinism, every so often you find a solution. When you find a solution, it's only good when F is exactly 0. that means that the probability of finding a solution is a Dirac delta function. You know, if you screw it up a little bit, sorry, in Norway we don't allow this. It has to be this way or not. So the probability density is a delta function which has a zero every time you pick up a solution, which is called classical solution, that satisfies equations of the motion, and otherwise not, right? And again, this phi it's a configuration of the whole neural network. It's not what happens on one side or anything. And now, to find probabilities, this is a probability density, to find the probability of certain pattern, I look at the floor and, I see green, green, red, red or something. I would like to know how likely this is. This actually is now a calculation. It's not, probabilistic exploration, because to compute a delta function, you need to use some, totally basic properties. So what is a delta function? It's a function that if you have an interval which includes it and you interval get 1. But if you're not in interval, you get 0. So it's very sharp. Now, if you decide that you're integrating over a linear function, like a times x, then you have to change your variables, and you find out that that integral is 1 over a. If you have a function, it'll only contribute to the 0. And when you look at neighborhood 0, the only thing that'll matter is the local slope, and you will find out that the value of integral over a function is 1 over absolute value, because this is positive, times derivative. And now we have 10 million dimensions, n, then this will be a determinant of a Jacobian, which is all pairs of possible variations. So that's what probability of a pattern is. I have to find this thing that, some reason I call orbit Jacobian, but basically I have to find a matrix that says if I, vary everything, because the index runs over all sites, all neurons. If I vary every neuron, I have to now find out how my, lattice state at some other site works. And that gives me a matrix of 2 indices. And basically, what this orbit does is I take my configuration, which is the legal one, I shake it a little bit. And, this tells me what the, variation, all possible variations in all directions look like. So that's, what Jacobians do. So basically, I'm taking my thing and I'm ending a little bit every place and I find it. So what this orbit Jacobian is, I perturb everybody all at once. So now, why is this good? Why am I suggesting this? I told you that Euclidean distance, I have my neurons, but I pairwise connect them and compare them without rhyme and reason. That's stupid. There's no reason to take differences of all neurons without any understanding how they're organized, etc. So that was stupid, but this determinant, this weight that shows up here has a magic property. It's a ratio of, let's say cow over cow, so it's dimensionless. So it's a matrix of numbers. And it has a property, and for that it's totally crucial that I'm looking at the solution of the system that's correct every place with correct boundary conditions. It has a property that if I go from millivolts measuring activity to dopamine, you know, that's a map of what my measurements were before in new units, that's a nonlinear map, etc. This has a property that these ratios don't change and determinant doesn't change. So that everybody gets, you know, the same determinant, no matter how they're doing the measurement, how they're perturbing the network. So that, you know, that's the key idea of this. This is intrinsic to geometry and dynamics of the system. And it's a number that you can associate that doesn't care, you know, how I did my construction, you know, what units I use, etc. So it's the same for me, you, and everyone. And for this, you have to read chaos book because, you know, I don't have time to prove it. But the basic idea is that if you have infinitesimal ratio of, you know, changes, if they are by nonlinear transformation locally, they change in the same way, then the local stretching will cancel out and the ratios won't, you know, determinant will be the same. So that's kind of the idea of geometry of this. But the main thing, this number, this made no sense whatsoever, but this is a number. So can we use that number to say how close am I to Eresfjord? You know, am I getting there? It's a matrix. And I made a deterministic matrix as a function. You know, at every side there is some polynomial. I take its derivative as some other polynomial, evaluate it for my solution. So it's a bunch of numbers. Determinant is a product of the eigenvalues. So I can write it as a product of the eigenvalues. And if I take a logarithm of the determinant, which there are many good reasons why I want to do this, then I will, you know, have instead of product of the eigenvalues of this matrix, this thing here. I can do this.
Can I ask you
Yeah.
a question about units? Because you seem to be implying that before you couldn't compare because things could be measured in different units.
Yeah.
But if I think of eigenvalues, the eigenvalues of a matrix come in the same units as the matrix.
Yeah.
So they might have units, the eigenvalues themselves.
So the matrix is a matrix of dimensionless numbers. I agree. If the matrix was in units 1 over time or something, then of course eigenvalues would have to inherit that dimension. But my claim is that this way of shaking up whole world produces a dimensionless matrix, which is intrinsic to the system, and you know, it's just geometrical property. So you understand this in time evolution. You know, what happens is if I have some neighborhood, the matrix produces some other neighborhood that's maybe stretched by some factor. And if I do this on a periodic orbit, no matter how I do this, it'll be the same stretching factor. And that's why, you know, I need to have correct boundary conditions for this to work. But, and, you know, I'm requiring faith right here, religion, because you know, time is short and I want to get the idea. Yeah. What do you say?
Here in the company.
Yeah,
So you're.
you know, the usual thing, I make it into sum rather than product.
No, but I mean, if you put here the logarithm of the eigenvalue and then you subtract the eigenvalues, the units cancel out. Yeah. So it's independent of the units.
Yeah, originally the units cancel out. So even if I had it in units, you're right. The ratios to determinants, units will cancel out. And now, why did I do this? You know, the Euclidean distance was stupid. There was no reason to do it, right? But this seems to be intrinsic to the problem. That if I look at, the likelihood of one pattern happening and the other happening, they're given by these determinants. If I look at their ratios, if they're close by, the same dimension because I'm on the same floor. If they're close by, then the eigenvalues will be close by. And if they're exactly the same, the eigenvalues will be the same. So I have a different way of measuring distance between two solutions. And it looks nicer because, it's intrinsic to geometry of the problem. It doesn't, and in special cases, if I really do it on regular, floors, I can use Fourier space method and I can show that, what I'm looking here are the eigenvalues and diagonalized, Fourier diagonal space, etc. But in neuroscience, it doesn't happen in numbers symmetry, but you do have eigenvalues. So now the claim is, I would like to say that I'm almost in Eresfjord because when I look at the hill pattern and I compute its stability, its likelihood that I've seen the pattern and the likelihood that I've seen the other pattern, I compare them in detail in terms of their eigenvalues, I can start saying that if these guys get to be close to each other, I have the logarithm of 1, which is 0, right? I have the same pattern. Now, this I did for determinism. There is no neuroscience or anything. I required that you give me a law how to do it, and then I do it. I'm doing okay. And, but actually, it's neuroscience, and, for me, the great inspiration was just looking at Sarah's work to think about this. And I'll try to, explain in a way that you've seen it already in this course. But basically, when I look at the probabilities of states of a neuronal system, every phi is a different activity, same architecture, but different activity. I can assign a probability to each, which I measure God knows how, like statistical algorithm, how often this pattern is seen or something. But in this deterministic formulation, I have explicit formula for this probability. It's 1 over this determinant. And if I take its logarithm, I get, that the logarithm of this probability is related to this kind of Boltzmann weight of the, if you think statistically. So, so this is just equality. And when I look at the, mean stability, but I average over the logarithm of the thing, this actually, already, this is called information in your method. Because, this is probability, this is logarithm probability. So you actually do this stuff. But, you think of it statistically. You think of it by, I produce probability distribution and I compare them. For me, this is always difficult to understand how you produce probability distribution in high dimensions. But this determinant of Jacobian is just calculation. It just says, if this is the law, this is how likely this particular pattern is in your world. That's it. That's called deterministic chaos or turbulence or whatever. And this object of comparing, two of these log of determinants is called Kullback-Leibler for you. And, the formulas there is a part that comes from normalization. And then there is average of these logarithms. Sorry?
In the previous, right? So what is different here from A deterministic situation.
You know, in deterministic situation, I just have this number, determinant of this Jacobian. Just number, I compute it. Now, you know, it might be difficult to compute, so Sarah, who is not, Sarah from Christina, you know, has to compute it for very large networks. And one way to do it is assume the network is random and you do, you know, fancy computations to compute this kind of determinant by looking at spectra of random matrices. That's one. In this context of deterministic laws, you don't do that. Nothing is random. You're just given a law, you find out stability of solution for your law, you compute this determinant, and that's it. It's not probabilistic. So, you know, one interpretation that you're used to is that you have many realizations of your network, and you try to find how frequent particular ones are. You bid them, you do something. And in the deterministic world, this is actually calculation. There is no binning or anything. And so it has a, you know, okay, it has a history in quantum mechanics. See, in quantum mechanics, there's something called WKB for people who have been taught quantum mechanics. Very early on in development of quantum mechanics, people realized that if you look at the classical trajectory of particle and add to it approximately a wave, quantum wave in a neighborhood, you can do a very good calculation of quantum properties. So, and then, you know, later in path integral and statistical formulation, people realize that these are saddle points of path integral is the extremal and they contribute most. So there's a long history of using this kind of methods. I'm just applying it here. You know, what can I say? But you can also solve quantum mechanical problems by, you know, producing lots of amplitudes and adding them up and doing some averaging, something like. You can do a Monte Carlo calculation of some kind. Yep. Yeah, I'm pretty much done because my thing says 3:33 was actually where the 3 minutes 33 seconds.
Here's what I found on the web.
And here is what I found on the web. What did you find? Okay. I'm much kinder. Sarah is not very kind to these people, but I'm very kind. I mean, yeah, everybody has a job, right? So, so the way you might have seen it is that, you know, you kind of have to average over some differences of the logs of probabilities. That's called relative information. And for example, in a nice paper of Gallego and Sarasole and other people, you know, they actually do explicit calculation. I mean, it's very standard. It's not the first time done here. But when you learn about Kullback-Leibler, you know, you start by first testing your own Gaussian because that's the simplest thing. You know how to integrate Gaussians, right? And when you look at why do they do this, you know, they have manifolds that they want to align. They want to, you know, get them to be similar. And one way to do this is to do a gradient descent in the distance where you try to improve your distance and approach your target. And, you know, it has few parts. One of them is slightly crude, which says, you know, two states, these are the center of two Gaussians, you know, I have to measure their distance, but I use a metric, which is the Jacobian rather than Euclidean metric. So it's a little bit better than the stupid thing we started with. There is a metric which is intrinsic to the problem. But then you compare this part, and then, you know, when you do calculation, you discover there's some extra pieces because when you do variational calculations, you have to make sure that the errors are quadratic, and that's what this extra piece does. And that's, it doesn't matter. But I just want to say, in the deterministic case, you can do this calculation from known matrices, which you compute for your system. And, if system is not too big, maybe it's doable in your case. But when you have a model, you might be able to do this calculation not in a probabilistic way of, producing some kind of probability distributions, but the way that, I do it. And almost there. The answer now is how close these two guys are. I say don't use Euclidean distance, makes no sense, but try to compare, how sensitive they are to jiggling. And that is intrinsic to the patterns. And therefore, I can assign an average distance in that space. Now, in a particular case of doing this in condensed matter physics where everything is uniform, this turns out to be something in brilliant zone of a crystal, etc. But you don't need that, Here you are in a different setting. There are no brilliant zone, there are no translation invariants, there are no crystal. And we are done. Thank you.